Okay, we can get started. Our first speaker is here, Zara, and welcome to the new Frontiers in Neutrinos session. And with that, we can let Zara take it away and talk about low energy neutrino physics at TIA.
Thanks for having me to speak, and thanks to everybody who managed to find this room and be here at 10 a.m. So I will talk about the TIA experiment, which in short is an advanced optical multipurpose neutrino detector that takes all the cutting edge developments in the target material and photo detection, creates a big large purpose detector, and as the output you can have a broad physics program studying neutrinos fundamental properties and astrophysical objects. Now this is a proposed experiment, so we need to really concentrate on this cutting edge developments, and there will be a dedicated talk from Tanner later today that will be covering this, but I will cover some of the basics. So how do we broaden the current physics reach? So what are we different that would allow us to go for new opportunities? So currently you can divide a lot of existing neutrino experiments into the scintillator detectors, the Neutrinos, NOPLAS, Juno experiments, and they're characterized by high light yield, low energy threshold, good energy and position resolutions. But they are limited in size by absorptions and the cost. Liquid scintillator is relatively more expensive than the water, for example. And they also have limited directionality. It's only in the recent years that we have the first indications how to get some directionality from the scintillation light. On the other hand, we have this big Cherenkov detectors, think SNO before the upgrade, before the field with liquid scintillator, of course, super K and hyper K. Here, the advantage is directional information. They can be very large because the water has very good, very low absorption, and the particle ID at the high energies. On the other hand, you are limited with the no access to physics below the Cherenkov threshold, and generally it produces much less light than the scintillations, the Cherenkov process. What we can do is that we want to combine all this expertise and knowledge that we have and create this water-based liquid scintillator detectors where we can get the best part of both detection techniques. Now, to cover the basics of what water-based liquid scintillator is, it's basically a mixture of pure water and oil-based liquid scintillator. Of course, water and oil don't mix that easily, so you do need to put a bit more chemistry here, and you need to use surfactants that are basically soap-like materials that basically hold the oil drop inside the water in this kind of micelle structure. If you simplify the way to look at it, you can think that, so you can think about the water advantages as attenuation length, scintillator advantages as the light yield, so how much light you have per energy of the particle. And if you tune the percentage of oil in the water, you can get more water-like or more oil-like water-based liquid scintillators. They will have different advantages. Now, of course, this is a very simplified look. That's why it has the basics comment. Of course, in reality, it's much more chemistry and much more nuance to this process. Besides having this knowledge of water and like water Cherenkov detection and the scintillation detectors, we can also play around with the separation of Cherenkov and scintillation photons and get maybe even extra more information by combining the two. So there are three handles that physics nature is kind to us to offer how to separate the Cherenkov and scintillation light. Of course, we all know that the Cherenkov light has a particular direction, so that gives us great tool for reconstruction of directionality, but also that's what the difference. Scintillation is very uniform, while Cherenkov is the direction. So you can look at it with the angular distribution lens. On the other hand, the timing-wise, the Cherenkov light is immediate, so it comes very, very fast, while the scintillation light first absorbs the energy of the particle and then re-emits. So there is a bit of a delay and then the wider timing distribution. So in order to separate the Cherenkov and scintillation light, we have large area picosecond photodetectors that have just been started to use in neutrino detectors. So Annie is the pioneer experiment to use it in the real live detection. And you can see that they have a very small TTS, so it's around 70 picoseconds, so it's much faster than PMTs. And even using a few of them will help you distinguish between the Cherenkov and the scintillation light. Finally, the wavelengths. So again, just the difference between the Cherenkov and the scintillation light. You can see the Cherenkov is quite wide, while scintillation usually is characterized by a particular width of the wavelengths. So here there is idea of using the dichroic filters to separate the Cherenkov and the scintillation light. And here Tanner again has been working on this idea for a long time. There are also red sensitive PMTs that can help you with the filtering. And generally, so again, you have another filter. Now you can use one of each methods to help you separate them, or you can try to use all of them and try to make your analysis of data even more sophisticated. So using all of these developments, these new ideas, and Tanner will talk about more about the R&D part of how close we are to actually being able to actually use it in the large scale detectors. We already have the prototypes that are planned and gonna go online quite soon. But where are we going with that? What does it offer to us in the long term to use all of this technology? So as I already mentioned, what I find personally the most attractive part about Thea is the multi-purposeness of that. You build one detector and you can cover most of the neutrino physics with one detector. So you have a lot of the natural sources from the astrophysical objects that you can detect with the Thea detector, and also neutrino fundamental properties that you can also tackle with the same detector. So I'm going to be covering mostly the low energy neutrino physics with the Thea, and Leon, who speaks after me, he will cover the higher energy part of the Thea program. So I will start with the solar neutrinos that are dear to my heart. The solar neutrinos are the neutrinos that are produced in the core of the sun. And when they arrive to the Earth's surface, this is how their energy spectrum and the flux looks like when they arrive to the Earth. Again, you have different sensitivity of water Cherenkov detectors and the scintillators, if they can cover different energy ranges. So again, with the water-based liquid scintillator, we're trying to push the capabilities basically of water Cherenkov into the scintillator range, and also increase the statistics that we can get from the solar neutrinos. The majority of the neutrinos and the energy that some produce comes from PP chain reaction. There is still one undetected small reactions that have neutrinos that are extremely low right here behind. But the rest have all been already measured with quite good precision, especially boraxino detector and boron 8 with the water Cherenkov detectors. And the CNO cycle has been measured only by boraxino detector 2 years ago. So you can see here some of the precisions with how they're predicted, but there's still something that we haven't finished the solar neutrino program. So one of the things, as I mentioned, CNO neutrinos has been measured only by one detector so far, and we can use a different background rejection technique in order to measure the CNO flux, which is always good to have different approaches in order to measure something. So the Thea, again, based on the directionality that comes from the Cherenkov light, offers an alternative background rejections, directionality based, and you can measure CNO neutrinos flux with a very high precision. So that CNO neutrinos are very sensitive to the solar metallicity problem. So we have very high motivation to measure it with a high precision. And you can see here some of the studies about how different precision of directionality affects our uncertainty on the CNO measurement. So this is very interesting for the astrophysical point of view. For the boron 8 solar neutrinos, we can have quite high statistics and low threshold. And boron 8 happens to be in a very interesting physics range where between the vacuum oscillations and matter enhanced flavor conversion. So you can see that by right now it's kind of divided, and all the low energies like PP, beryllium 7, PAP neutrinos, they are in the low energy, so where you have mostly vacuum oscillations, while boron 8 is mostly, the measured one is mostly in the matter-enhanced flavored conversion. And this is where, for example, all the solar neutrino problem was with, you can see this is the survival of electron neutrino, and you can see that it's around 1/3 of the generated neutrinos. What we are interested in this bit in between. So in this bit in between, there is a lot of potential for physics beyond standard model. And there's some non-standard interactions, sterile neutrinos, that would modify the way this probability changes between these two modes. So if you measure boron 8 with the lower energy threshold and high statistic, you can probe this region, and that could be very interesting for neutrino flavor, neutrino fundamental properties. This was the solar neutrinos. Now moving on to the other astrophysical object that is very near to us, the Earth. The geoneutrinos are neutrinos that are produced in the radioactive decays from uranium, thorium, and potassium. Uranium and thorium are the ones that are actually producing detectable antineutrinos. The detection channel is inverse beta decay that has a particular threshold with which we can detect it. Currently, there are only 2 measurements in the whole world, Poroxeno, Italy, and Kamon, Japan. So they are both scintillator detectors, because if you, the energy range of geoneutrinos is quite small. So you can start detecting it at 1.8 MeV, and the whole range goes a bit more than 3 MeV. So it's really narrow energy range, and it's very low energies. That's why the water Cherenkov detectors haven't been able to measure it so far. But so we can measure these antineutrinos, and they are directly, as you can see, they produced in the basically radioactive decay along with the energy. So you can basically have a almost straightforward connection between the number of antineutrinos that you produce in these reactions and the energy that the Earth produces itself, the radiogenic heat of the Earth. So the total of the radiogenic heat is known, kind of. So the total, we know this, I don't have it on the slide, but 42 terawatts, but how it's divided between the secular cooling, so the leftovers from the Earth formation, and the radiogenic heat, what is produced in this radiogenic reactions, is still not known very well. So that's why where neutrinos can come in, because this is actually a very direct measurement of what can happen inside the Earth. We can have some of the measurements from the crust, because people are actually doing the holes in the Earth and measuring the heat that's coming up, but you cannot really drill down to the mantle. And that's where neutrinos can actually, if you manage to separate the mantle signal, can give you actually the information about the reactions that are happening in the mantle. We have a new study on the sensitivity of Thea-2 geoneutrinos. We have studied how we can measure both geo and reactor neutrinos, because they're both antineutrinos, so we can detect them in the same way. But since they have different energy spectra, we can perform the feed and extract the values of each of them. So you can see that we have very high sensitivity to both of them. We have also in this way, we assumed the ratio of uranium and thorium from the geological models, but we also made studies when we don't fix the ratio and let both uranium and thorium component free, and we perform the feed like that. And here you can see that we still have very high precision to uranium, but a bit smaller to thorium, but we still can measure both of them, and we can measure the ratio of the two that are the more important geological factor that a lot of geological models are using. And that's something that we hope where geologists and physicists can work together, and that has become interdisciplinary field since few years. The next up is the supernova neutrinos. We have the 2 kinds. One is, of course, supernova burst neutrino. That is, if we have an event that happens, the supernova is around 10 kiloparsecs, and we observed superneutrinos. Here, last time it happened, it was 1987. So we're due for a new one quite soon. So we hope that we can see one. And at that time, we had only 3 detectors that were able to measure neutrinos. Right now, we hope that we'll have much more detectors online when that happens. And we can do a lot of analysis with individual detectors, but also a lot by combining the neutrinos, the number of neutrinos that we detect with different experiments. So let's start first with the Thea itself. You can see that we will be able to detect both antineutrinos, inverse beta decay, a bit much smaller normal neutrinos with electron scattering, but we can have these different channels of the detection of supernova neutrinos. Again, we will have low energy threshold, expect good energy resolution, and directionality. So here you can see some of the studies about the supernova pointing and how that can be helpful. On the other hand, for example, if Thea is placed in the Dune module of opportunity, it will be even higher statistics of neutrinos. That is better with a different technology, different kind of detector. So you can do some of the combined studies overlapping and cross-checking some of the systematics. On the other hand, you have several experiments that are on the other side of the world. Juno in China and Hyper-K in Japan will be online at that time. And you can study Earth matter effects, how the neutrinos oscillate when they're going through the Earth. And there are also, if you have high statistics, there's a possibility you will see the pre-supernova neutrinos. So then you can also help other detectors to point, for example, like gamma ray detectors to point into the direction of the supernova. But besides that singular event that we cannot predict what is going to happen, we also think that there's a diffuse supernova neutrino background. So it's a diffuse isotropic flux of all the neutrinos from all the supernova explosions in the history of the universe. And it has not been experimentally observed yet, but we are quite hopeful that it's going to happen quite soon. Here again, we have the advantage of the Thea detector through Cherenkov and scintillation ratio, that the separation and then ratio, as you can see, the main background for the diffuse supernova neutrinos are atmospheric neutrinos. And you can see by the looking at the Cherenkov scintillation ratio, you can separate them statistically quite well. So we expect that we'll have the 5 sigma discovery in around 8 years if you build a 25 kiloton Thea, and around 2 years if it's 100 kiloton Thea. This will generally add substantial increase in event statistics, even if we already have the observation by the time from Super K and Juno as well. Finally, to conclude, so again, I covered only low energy program of the Thea detector. Leon will follow up with the high energy program. And as you can see, we have quite a lot of advantages by combining the Cherenkov and the scintillation techniques, knowledge, and the tricks all we have by also separating and combining the Cherenkov and scintillation information. Just a few examples to remind you, we have directionality in solar neutrino analysis and probing the unexplored energy range. We can have the geoneutrinos with quite high precision, also extracting separately uranium and thorium and their ratio. We can have the very high statistics and very rich physics potential of kind of analysis you can do with the neutrinos that are generated with the supernova bursts. And of course, the diffuse supernova neutrino background is very interesting because we haven't observed it yet. So we don't even know how much physics we can get from there. So thanks a lot to the whole field collaboration. And of course, all the questions are very welcome.
Thank you so much, Zara, for the excellent talk and also for sticking very nicely to the time. We do have time for questions. So I'm looking at Zoom. I haven't seen any hands raised. Anything in room? Okay.
Test. So awesome talk. I love that it's such an interesting like way of attacking such a broad physics program. So it's really cool seeing all these things come together. One of the things that was on your low energy list was neutrinos double beta decay. And I was just wondering if there are handles within Thea that allow you to sort of disentangle the various different low energy signals. Like, for example, you talked about the excellent solar neutrino program, but I assume that would become a background for neutrinoless double
Exactly.
beta decay.
Yeah.
Is there something in Theia that really helps you sort of like separate out those two signals?
Yeah, no, exactly what you mentioned with the boron 8 being one of the major backgrounds. And there, what we are using here for a signal that we can use for the background. And we have the studies as well in the Theia white paper that I should probably link also on the conclusion slide, but they are throughout the slides. We have the estimation of the sensitivity of Theia to neutrinoless double beta decay, and where there's a plot of how boron 8 uncertainty influences our sensitivity of neutrinoless double beta decay. So you got it. You got the answer as well.
Okay, any other questions? Any questions from Zoom land? Okay, well, let's thank our speaker again.
Thank you.
And next up is Leon. Did I say that correctly? And as he gets set up, and again, for people on Zoom, if you have questions, feel free to raise hands or type in the chat. And I'm watching Zoom as well as the room.
Take my mask off. So I'm okay with that. Oh yeah, well I fog up otherwise, so I can't really see what I'm doing.
Let's test your microphone too.
Maybe. It's all right. We're going to look. Okay. Can everyone hear me? Is that good?
Can Zoom people
Hello,
hear?
Zoom? I think we're good.
I think it's good.
Are we
Yeah.
good?
Yep.
Am I
Go
still
ahead.
good? Here we go. Okay. Right, we're cooking on gas now. Okay. So yeah, I'm just going to follow the excellent talk by Zara and smoothly transition into the high energy physics program within Theia. So yeah, first of all, I'll just highlight the Theia collaboration. I'd like to talk about its size and its international effort. Zara spoke excellently about how WBLS can, we get the benefits of both Cherenkov and scintillation light. So I want to really focus on that, how that will help the high energy program. Of course, you can't have a neutrino high energy program without talking about long baseline physics. I'll then talk about the nucleon decay searches that are possible, and then just briefly talk about the contributions that it can have to atmospheric neutrino measurements. So yeah, the Theia collaboration, I think it's important to stress, is a large international effort. We have now, over the last 10 years, we've gained collaborators. We've now got over 80 collaborators from 10 countries. So it's becoming a real global effort from 38 institutions. And this, combined with the novel nature of WBLS, it really does offer an exciting expansion to not just the low energy regime, but also the high energy neutrino community. So what is WBLS? This has already been discussed, but I know a fair few people find it hard to find the room, so it's good that I still put it in. So we've got WBLS is water-based liquid scintillator, and it's an aggregation of water and your sort of traditional oil-based organic liquid scintillator. In general, when you mix oil and water, it doesn't work very well, so we have to introduce a molecule, a surfactant, which has a hydrophilic head and a hydrophobic tail. So the hydrophilic head wants to stay in contact with the water component, and the hydrophobic tail sequesters itself within the liquid scintillator. So what you get are sort of nanometer scale droplets of liquid scintillator that homogenize throughout your detector medium. And so in doing this, we can get both the benefits of your liquid scintillator medium and the water. And putting all this together, it gives Theia a brilliant capability of becoming arguably the most far-reaching, wide-ranging neutrino experiment ever built. And we have just a nice little visualization in the bottom of the Theia 25 detector. So you can just see that there. Okay, so how will WBLS specifically help the high energy neutrino effort? So you have the two sections here. You have your traditional water Cherenkov detector and your traditional scintillator detector. And then you've got WBLS, which is greedy, that wants to do absolutely everything. So your water Cherenkov detector, it benefits from particle directionality. We've seen how this can be important for the low energy regime. It's low cost, safe to use, and has long attenuation lengths. This is particularly important in the high energy regime because we want to get large statistics to try and tease out the difficult problems in the high energy regime. And so if you have low cost and long attenuation lengths, you can build huge detectors and you can get large statistics. Then you've got the scintillation component. So you get a high light yield. This improves your energy resolution. We'll see how that helps tease out these answers. It means you've got you get a low threshold as well. So we don't need to worry about sort of below Cherenkov threshold particles. We can still see these. This again can help energy resolution because you can have hadronic final states coming out of your nuclear interactions that you can then tag and measure and understand. And you get excellent alpha beta discrimination capabilities. So you put all of this together, you can build huge detectors with excellent energy resolution, and you can try and find the answers to some of the very difficult questions. What is Theia? It's kind of a two-phase program. So Theia 25 is a 25 kiloton, 17 kiloton fiducial volume cuboidal design that's designed to fit alongside the Dune FAR detectors to give you a complementary FAR detector with different systematics within the same neutrino beam. And then Theia is the end goal of the Theia collaboration. And this is an ambitious 100 kiloton upgrade to the idea. So we have a nominal right angled cylinder with around about a 70 kiloton fiducial volume. So we're talking about an absolutely huge WBLS detector. To try and take advantage of the scintillation and Cherenkov light, we'll use fast photo sensors so we can take advantage of the timing that Zara discussed, and then employ other photon sorting techniques as well. And it's this combination that enables it to have such a wide ranging program, making it, and it's a bold statement, but I would say the most far-reaching neutrino experiment ever built. Okay, so I've sort of given you some motivation. What are the unresolved issues of long baseline physics? I think you can arguably say there are three main unanswered questions. So what value does the CP violating phase take? What is the neutrino mass hierarchy? Do we have two light neutrinos and a heavy neutrino? Or do we have one light neutrino and two heavy neutrinos, making this very unique fermion in the standard model? And then finally, what octant does θ23 lie in? Is it above or below 45 degrees? The reason that this is so tricky, these are so tricky to measure, is that within the PMNS matrix, you get parameter degeneracy. And this is highlighted by your, in this case, the electron neutrino appearance signal, where you can see you make one measurement, effectively the number of electron neutrinos you see in a muon neutrino beam. In here, you've got matter effects, you've got a CP violating phase, and then sprinkled throughout, you've got a fair few θ23s. And disentangling all these needs novel and different approaches, and this is where Theia can come into its own. So first of all, the mass hierarchy. Theia, this is Theia 100, will be able to determine the neutrino mass hierarchy within 7 years, assuming 3.5 years neutrino, 3.5 years anti-neutrino mode. And the reason it's able to do this is great work by many Theia collaborators. And in recent years, we've got vast improvements in neutral current background rejection, particle identification, and the use of multi-ring events. So for this analysis, we use a 9-sample likelihood fit, and we assume the same beam-related systematics as the Dune CDR. So you can see even the smaller 25 kiloton Theia performs comparably to a Dune module, and then the 70 kiloton fiducial volume Theia, you effectively you find the mass hierarchy with relative ease. And an important point for this analysis is this assumes just a water Cherenkov detector. It's not throwing in the fact that we've got organic loading. We have these new photon sorting techniques. And if you do this, you improve your efficiency further, your purity further, you improve your particle identification. So this is very much a conservative estimate of what the Theia detector can do. Okay, so Theia 100 also has the capability to reach 5 sigma CPV determination. Obviously, it depends on the value of delta CP and how kind nature is. If CP is maximal, then we can reach this 5 sigma limit. Of course, if it's the closer it gets to 0, the harder this becomes. But nonetheless, this will make it, alongside Hyper-K and alongside Dune, a world-leading CP violation measurement. And then just for completeness, on the right-hand side here, we have just some of the spectra that show the use of different multi-ring events that can get folded into this analysis. And then the final piece of the long baseline puzzle, Theia was going to add to the determination of θ23. So this time we would use the disappearance channel, and it will then add to the data set already existing from T2K, NOVA, and MINOS. The beauty of WBLS here is that you then get different systematic uncertainties, different baselines, and this is how it can add to the global picture of trying to determine this tricky PMNS value. Something that I think is really quite important to stress is that you can introduce atmospheric neutrinos data into this fit. And then because you've got atmospheric neutrinos that come from different angles with different energies, and as such have different baselines, the Theia can then start to break the degeneracies seen within sort of some of the existing long baseline measurements. We can start to constrain the matter term within the nu mu disappearance signal and start to pin down θ23 so that we can try and find out which side, which octant this value takes. So moving from long baseline to nucleon decay, the combination again of the scintillation and Cherenkov properties gives Theia a unique advantage in many different channels. So we'll talk first of modes in which low thresholds are not essential. So we, for example, P to E plus pi 0. So this is the area where Theia, you could argue, struggles the most, but nevertheless, because it is a huge water Cherenkov detector, it still can produce world-leading measurements. For modes in which you've got below Cherenkov threshold mesons, this is where Theia starts to come into its own, because now you can, whereas a water Cherenkov detector will not be able to see, for example, in this case, the K plus, Theia is able to perform coincidence tagging, so you can see the production, the decay, and the decay of the decay products of the K plus. And so when you put this together with its huge mass and this combination of water Cherenkov and scintillation, you can see that the 100 kiloton Theia will become the leading nucleon detector in this mode. Nonetheless, this isn't even the best mode for Theia. A good example where it really truly is the preeminent detector is for invisible nucleon decays, such as neutron to 3 neutrinos. So here it's got this huge volume combined with the low energy threshold. So you have, for scintillator detectors, you can have the low energy threshold, but as again Zara said, you get self-attenuation, so you can't build detectors with such mass. In these nucleon decay experiments, you just need as many nucleons as possible. And so this is where Theia really does thrive. Add to that the depth at the far detector site means that essentially as soon as you turn on Theia, it becomes by a few orders of magnitude the best nucleon decay experiment in this regime. Oh, 5 minutes. Okay, perfect. 5 minutes. So I'll just briefly look at atmospheric neutrinos. So I alluded to them earlier, and how if you add your atmospheric neutrino data set to your accelerator data set, you can break the θ23 degeneracy. So we can try and get rid of the Minos smile in that plot and start to pick which side and which octant θ23 takes. But and this is not an exhaustive list, but there are many other potential contributions to the field. So we could start to look, as Super K has done, at the east-west geomagnetic effect, how the Earth's geomagnetic field affects the flux from different directions. We can look at solar wind modulation. So the sun has a solar wind cycle of around about 11 years, and this has implications for below GeV atmospheric neutrinos. And so we can see how that modulates on this solar timescale. And then finally, absolute flux determination. So there are many measurements that have looked at the absolute flux, many different models. In spite of this, there's still around about a 15% uncertainty on this measurement. So Theia, with its huge size, can start to drive down that uncertainty for the benefit of the entire atmospheric neutrino community. And conclusions, I think I've got another minute or so. So Theia is a proposed 100 kiloton experiment that, and I'll say it again, has the capability to become the most far-reaching neutrino experiment ever built. We use WBLS to take benefit from both Cherenkov and scintillation emission. In the CP violating regime, Theia can potentially get a 5 sigma result, depending on how kind the nature has been. It will determine the mass hierarchy. It will start to narrow down the value of θ23. It will have great implications for atmospheric neutrinos and become one of the preeminent nucleon decay detectors. So thank you.
Yeah, thank you so much for the excellent talk. So we have time for questions. Okay.
Plenty of interest.
She raised her hand first, I think.
So this sounds great, almost too good to be true. So what are the downsides? What are the hurdles that you have yet to overcome in order to make this the sure thing?
That is an excellent question. And I can kind of push it over to Tanner because he's about to give a talk on this, but I will refer to it somewhat. So obviously it's a new detection medium. I don't really have any nice pictures. We'll just leave this one up. So obviously it's a new detection medium, and that does come with some challenges. So producing it, keeping optical clarity, purifying everything, understanding the subtle interplay between Cherenkov and scintillation light. Can we get fast enough photosensors to try and separate the signal as much as we like? As Tanner will show, we have done this. So basically the main problems come with using a new medium. That being said, unlike, for example, liquid argon, which is an entirely new medium, we're combining two media that we know very well. We know scintillation very well. We know Cherenkov emission very well. So although there are some challenges, in many ways, there are easier hurdles to overcome. And to try and solve a lot of these, we have smaller scale experiments. So we have a system at Brookhaven that's going to look at filtration mechanisms and stability over time. In Annie, we're going to put a WBLS volume so we can see how it does behave in a neutrino beam. And then we've got EOS, which Tanner will talk about, that will look at many different other issues as well. So it's tricky, but over the last few years, we've made significant strides.
Lauren is next.
Hi, Lauren.
Hey.
Could you maybe go back to slide 9?
Absolutely.
Where you're talking about the oscillation sensitivities. So this looks really great. Can you say what, if anything, you're assuming about a near detector?
Yeah, so this, so one of the issues in sort of the Dune
Yeah.
regime is that we don't have a near detector. Something that would be needed would be to install a near short baseline detector so that we can start to constrain cross-section flux, etc.
Okay.
Systematic. So this is under the assumption that we have a good handle on these with similar systematics that Doom will have.
Okay. And is this assuming like a Theia style water-based liquid scintillator in your detector, or
Yeah, so ideally you would have a mini Theia.
functionally identical?
So then we've got 3 Theias, right? We've got an even smaller one.
Okay.
But you can get away to some extent with just a water target.
Okay.
Because for the high energy regime, you don't necessarily need the light yield for the low energy regime. So you can have a smaller scintillation load in. And so your detector is effectively 99% water.
Okay. Okay. All right. Thanks. That's helpful.
Okay, so we have one more question in the room. So Josh, I know you're on Zoom,
Right.
but we'll take this one question from the room and we'll come to you and that's it.
Hi, very nice talk and informative talk.
Thank you.
My name is Jay Yu. I'm from UT Arlington. Just one comment on this. This particular plot assumes that Dune 10 kiloton has a prism in it too, right?
Yes.
So there is a systematic control
Yeah. So it
using the
follows the
prism.
Dune
So
CDR.
you're doing exactly the same thing. Okay. In any case, so this Theia 100, what's the timeline that you guys keeping in your mind? Is it?
So yeah, that's the $1 million question that may well be above my pay grade, so to speak. As far as I'm aware, and Zara can correct me if I'm wrong, there's no specific timeline for Theia 100. Theia 25 would be, ideally to install it when the fire detectors are doing.
So this is sort of a
module.
module of opportunity style.
Yeah, Theia 25 is model opportunity style. There are talks about, so we had one of the panel sessions this week here at Snowmass of when we would need to put a proposal for space for Theia 100. And there are several, so there are active conversations about it with SURF or SNOW, for example. They're also considering apparently to go deeper and increasing the available space. So that's something that is actually this Snowmass process is kind of for, where we are all of these people from different fields are in the same room and we can talk about it. So the timeline of putting the proposal in is quite soon if you want to have it in a decade or so. So it's something that also the timeline, it's kind of a back and forth conversation between how much time the underground labs need to create the space and who wants to pay for this, and this kind of high level decisions that need to be made.
Okay. Now my follow-up question then is, but let me finish.
Okay, go ahead. Yeah.
Yeah, one of the important things and the strength of the Dune detector is that it can actually perform beyond the standard model physics, right? For instance, the stereo neutrino searches, especially for using far detector, and also dark matter searches that are coming from boosted dark matter searches come from the sun and stuff. What's the impact of this particular detector to that kind of physics?
Yeah, so in many of the regimes, they do have complementary approaches. So we've looked at so supernova searches, for example, okay, not beyond the standard model, but because you look at either antineutrino or neutrino modes, you get complementary systematics. With regards to beyond the standard model, I would say that the area that Theia really benefits is CP violation. You can see here that which is, I would say, it's blue ribbon project. You can see that it would far exceed Dune. So I think the combination of the two together, if you have a similar site, they can work in tandem to try and tease out these differences.
Right. So I'm sort of making a suggestion in the Theia group that it may be a useful thing if you can generate, for instance, a plot for, say, stereo neutrino sensitivities.
Mm-hmm.
Depending on what the systematics is, that those sensitivities could be impacted quite a bit. So if this detector can actually sort of reduce the systematics, I mean, of course, the biggest thing is the flux systematics, but I think generating such plot is going to be also very helpful.
Okay. Yeah. Thank you.
Okay, thank you. So we do have time for Josh if you would like to ask your question, but if you'd like to skip.
It was a quick comment, actually, more than a question maybe, but we saw from Mark's plenary talk the other day that Nova and T2K have different answers for the mass hierarchy for CP violation. And we should consider, in the event that Hyper-K and Dune also disagree, what the added value would be to having a detector like this, which has a similar target to what Hyper-K has, next to Dune in the same beam. It would be, I think, a tragedy for the field if we sat with an unresolved difference between these two and then had to start building, a program for 20 years to figure out who was right. And so thinking about this sooner may be very helpful. Thank you.
Thank you, Josh. Okay, so we're going to move on to our next speaker, and we, given all the excitement, we're running a little bit behind. And as our speaker gets settled, one thing that I'd like to mention, if you have a question in the middle of talk, if that's okay, we're going to wait and come to you once the talk finishes, given the time. But thanks, everyone. Okay, so our next speaker is Kevin, and he's gonna take it. He's just gonna take it over as soon as he's ready.
Yes, thank you. Let me see if captions are coming up to make sure the mic is hot. Okay. Great, thanks. Yeah, so the title of my talk is Accelerator Neutrino Oscillation Experiments, This Generation and Next. Whoops. Okay, gotcha, thank you. Okay, but I am missing probably an important adjective that should go in front of this, which is, I'm really gonna be discussing the long baseline accelerator neutrino oscillation experiments. I'm not gonna touch any of the short baseline stuff. And because we've already heard so much about Thea, I'm also not gonna talk about Thea. And maybe before I get into it, I just wanted to say that I've really been enjoying these early career sessions. I think it's been really cool to, see what the early career people are into and being able to engage with them and see what's interesting. A lot of discussion on some of the more technical aspects of the early career work, which has been really cool. This talk's going to be a little different, kind of more general comments about the field moving forward. So maybe you can sit back and relax a little bit, but I hope you enjoy the talk nonetheless. Here we go. Okay, so yeah, just a bit of an introduction. So the operating long baseline accelerator neutrino oscillation experiments in the next decade or so are going to be transitioning into the kind of the current generation into the next generation as we enter the precision era. And the experiments that I'll be discussing for the current generation are the T2K experiment in Japan and NOVA here in the US. And then the next generation will be the T2 Hyper-K and Dune. So both pairs of these experiments offer complementarity in the measurements that they can make, which sort of gives you this situation where the information from both together is more than just the sum of the parts. So I'll talk a little bit about that in the presentation here. And another point that I want to stress before I talk about the current generation and then the next generation is that trying to get everything we can out of the experiments that are running right now is obviously a very important exercise in its own right. It's kind of going to be the legacy that these experiments leave behind as we move forward. But it's also a very important exercise to inform the process of bringing up these next generation experiments. And then, yeah, just before I get into it, a disclaimer that I am a collaborator on T2K and Dune, but today I'm speaking just as a member of the neutrino community. So the usual comments about any misrepresentations are my own. Okay. So I'm sorry, I know everyone is sick of seeing cartoons like this. I know you've seen it all week, but for completeness, I need to kind of describe here. long baseline accelerator neutrino oscillations. So you start with accelerating protons, and then you hit those protons on some target to produce hadrons. You can focus those charged hadrons, and here I'm drawing the pions, which is the predominant component for us. You can focus them and sign select, crucially, with magnetic horns, and then you allow those pions to decay in flight. You get muon neutrinos and muons, and the muon component will be absorbed, and then you are left with a neutrino beam that will continue. You put a near detector in the path of this beam to measure what the flux is that you generated, and also make cross-section measurements. And then you let that beam travel some distance, which depends on the energy, and then you make measurements at a far detector to try to infer what kind of oscillations happen. I want to make note of just a few features of using accelerator neutrinos for these oscillation measurements that are, kind of add some, I think, are appealing features of using accelerators. And the first is crucial to studying delta CP and neutrino oscillations, which is that you can, by changing the polarity in your magnets, you can select either positive or negative charge pions, and that allows you to operate in either neutrino mode or anti-neutrino mode. So you can measure neutrino oscillations and anti-neutrino oscillations separately. That gives you a good handle on CP violation. It's also a tunable neutrino source, so you can play with the details of this setup and the energies of your protons and the details of your focusing system to tune what kind of energy spectrum you get from your neutrinos. And there's also, kind of along with this tunable business, you also have what's called the off-axis trick here, and experiments will utilize this in different ways, but just due to the kinematics of the pion decay, you'll see a different neutrino flux depending how far off-axis you are from the inferred direction. So let me, go the right way, not the wrong way. And then, of course, we use this setup to measure the oscillation parameters. And here I'm showing, this is the dune unoscillated flux in blue, and then an oscillated flux in orange. And the way that some of the oscillation parameters imprint in the oscillated neutrino flux is the height of this dip right here is proportional to sine squared 2 theta 23, whereas the energy at which that dip occurs gives you a handle on delta m squared 32. You'll notice that there's a 2 in front of this theta 23, and that presents this octant degeneracy in the new mu channel. And you can see that in this plot on the right, which is a sensitivity plot from Dune, which is coming from a 4-flavor fit, but you can see this. Yeah, sorry, the captions. You can see this degeneracy for upper and lower octant. Thank you. But this degeneracy can be broken if my pointer. Sorry, I think moving the captions. Cool. That's you can. Okay. Yeah. Perfect. Thanks. Yeah, that degeneracy is broken if you look at the Newey appearance channel, which has a term that's proportional to sine squared theta 23. So now the 2 is removed, and you have some sensitivity to which octant theta 23 lies. Of course, in the Newey appearance channel, you also have sensitivity to delta CP, which is one of the main targets for future generation experiments and current generation experiments. Okay. Right. So in terms of the current generation experiments, I mentioned there were two. There's a T2K, which sends neutrinos from the east coast of Japan over to the west, from Tokai to Kamiokanda, and Tokai to Kamioka, where there is the FAR detector. It has a flux peak around 600 MeV, and given what we know about delta M squared 3.2, that puts the baseline at 295 kilometers, gives you the dip where your flux peak is. Another feature of having the flux peak down at this relatively low energy is that you're dominated by the relatively clean CCQE interaction mode. You can compare this with NOVA, which has a higher energy, which peaks around 2 GeV, correspondingly longer baseline, but this higher, and we saw in the last talk that the longer baseline can give you some sensitivity to the hierarchy, which is another important kind of outstanding question in the neutrino sector. But you now have a broad mix of interaction modes with resonant pion production and deep and elastic scattering. So you need to really understand your detectors and be able to reconstruct the full event from all these different particles that are going to be coming out of your neutrino interaction. NOVA does that energy reconstruction calorimetrically. NOVA, on the other hand, uses the lepton kinematics they reconstruct to reconstruct the energy. And it's also true that the FAR detector for T2K and NOVA both sit off axis. T2K at 2.5 degrees, NOVA at 1.5. And T2K has rather different near detector and far detector technologies, and whereas NOVA has functionally identical near detector and far detector technologies. And with this in mind, it sort of manifests itself into having different analysis approaches as well. So T2K takes the approach of using the near detector to constrain systematics that are present in a model that is used to make predictions at the far detector. I kind of struggled to. NOVA has a different extrapolation procedure to use the near detector in their analysis, and I struggled the way to write it in just a few words that would fit on this line. But it involves looking at your near detector data, unfolding that near detector data, accounting for differences between the near and the far, and then forward folding and making a prediction at the far detector. So this is really a tuning procedure, and it's not really a fit. Whereas in T2K, you really fit your near detector data to the model and then use that constrained model to make predictions at the far detector. And one of the points I wanted to make with this big table is that, while both of these experiments kind of have this, the same basic principle with the setup, there are, if I go the right way, there are, some significant differences in the details of how that comes together. And that can be leveraged. Okay, so comparing some of the results here, I was using these plots. So or the plot on the left here is the disappearance parameters. And I want you to focus on the NOVA results in solid black, and then T2K here in dashed red. So pretty consistent picture right here. And the appearance channel, this has gotten, I guess, more attention in the community. If you look at the normal ordering, there is this tendency for the experiments are kind of picking up at different areas of the phase space. Some people describe this as tension. I personally don't think that we really have strong evidence for any tension yet. We just don't have the precision and the statistical power to claim any significant tension. It's also true that in the inverted ordering, there is quite a consistent picture there. And it's important to point out that at the moment, neither NOVA nor T2K have a very, very strong preference for either normal or inverted ordering. So really, if you kind of by eye marginalize over both of these hierarchies, you see that, you can't have too much tension when, you're pretty flat across the parameter space. Okay. So I wanted to make the point that complementarity can help by when you consider both of these data sets. There are degeneracies in the parameter space that was mentioned in the last talk in terms of mapping your observables to oscillation parameters. You can see that by looking at these by event rate plots, where you have the number of neutrino-like nuis and the number of anti-neutrino nuis that show up from your neutrino beam. And each of these ellipses carves out all the values of delta CP. And then the different ellipses are using different parameters for sine squared theta 2, 3 in the hierarchy. So the dashed and the solid are comparing the inverted hierarchy and the normal hierarchy. So you see with T2K with the relatively shorter baseline, there's not a lot of separation here. Whereas in NOVA, you do get separation. So there are degeneracies for both of the individual experiments, but they overlap in different places, right? So if you pick just one of these points, let's say inverted hierarchy, minus pi by 2, you see that for T2K, that's degenerate with the normal hierarchy in a different place than it is with NOVA for different values of delta CP. So this can be leveraged when you do analysis that considers both of these data sets. And one way to see that actually is from looking at joint analyses or global fits. And this is a result from NewFit recently. And the only point I wanted to make, there's a lot going on here, but again, if you just look at the NOVA, T2K, and then LBL combined, which is supposed to be the joint analysis between NOVA and T2K, I wanted to point out that both NOVA and T2K prefer the normal ordering on this panel. But when you do the combined analysis, you actually have your best fit showing up in the inverted ordering. And you can kind of see that in these plots, right? So both of these have best fits in the normal ordering, but just by eye, if you try to look at, what's the most consistent point, you might pick out this inverted ordering point right here, which was also, very consistent. Okay. NewFit's great. It's great that people are, working to look at the global picture with all of this data. But T2K and NOVA are pursuing a joint analysis themselves, and this is good because you can leverage a lot of the sophisticated analysis tools and the considerations and development of systematics that each standalone experiment has put the hard work in over the years, and you get that complementarity as well. So yeah, it's been a while. We have created a working group to pursue this joint analysis, and we're targeting a release of this analysis this year. So please stay tuned. Here's a picture of the last picture I could find where we had a workshop in person. It's back in 2019. A lot of people here. I wish it was this many people working for the past 3 years on this, but of course, all these people are very busy working on other things as well. Whoops, keep wanting to go backwards. Okay, and then quickly, because I know I'm running low on time, the next generation is a similar picture here. So now you have Dune in the US and then the T2 Hyper K in Japan. Similar difference in the approach of different energies. So T2 HK is still at this 600 MeV, same baseline, CCQE dominant interaction mode. Dune is actually going to be on axis and has a broadband beam. It goes up to 5 GeV, very long baseline. And because of this broadband beam, you have a broad mix of interaction modes. So you need a really performant FAR detector to see all that information, incorporate it into your energy reconstruction. And that technology is going to be liquid argon time projection chambers, at least for the first 2 modules. Both these experiments are going to have just very intense neutrino beams. So T2HK will go up to 1.3 megawatts, and Dune will start by getting up to 1.2 megawatts, and then hopefully we'll be able to upgrade to 2.4 megawatts in the future. And because we'll have these really massive FAR detectors and really intense beams, we'll have a lot of statistics, which means that systematics are all the more important. So it's really critical to have, very performant near detectors. And let me just move on from there. So yeah, I wanted to have a couple slides just showing you as you move from T2K to T2HK in this case, what kind of boost in sensitivity you're getting. These two plots aren't exactly apples to apples. This is the recent results from T2K coming out of that were presented at Neutrino 2020. So this is an actual data fit here. And you can see if you go up to the kind of 5 sigma level, there's just 1 point maybe in your parameter space that you're able to say maybe not. This is now, of course, we don't have a data fit for T2HK yet. So this is an Asimov fit, simulated data that you're fitting. This simulated data is considering a true delta CP of 90 degrees, not the negative 90 degrees that T2K seems to favor. And the fits here are assuming that are assuming the normal hierarchy. And you can see I just wanted to draw this 5 sigma line now. So here you'll be able to rule out quite a bit of oscillation space, parameter space. Okay. And then a similar slide to try to show the added sensitivity you get going from the NOVA to Dune. Here's that by event rate plot where you can see you have relatively good separation of the normal hierarchy and inverted hierarchy curves. But when you go to Dune, these really get very separated, and you don't have any overlap here, any degeneracy. And this actually isn't really doing Dune justice, showing plots like this. Because this reduces the experiment for the Newey appearance, at least, to a counting experiment. And there's a lot of spectral information in Dune's wide band beam. You can see this little peak down here at low energies. You actually can see some of your second oscillation maximum. But just to kind of illustrate the point of the much longer baseline gives you this degeneracy breaking. Okay. And then here are some of the sensitivity plots that are coming out of the Dune studies. So again, with those ellipses being very separated, you see that you'll just get the mass hierarchy 5 sigma easily, very quickly. And then for delta CP, you also have a lot of sensitivity to observing CP violation for a wide range of values of delta CP at very high significance. And then this is kind of a nice plot just to kind of show, these next generation experiments are really adding to the precision measurements we can make. This dashed line is the current resolution we have for delta m squared 3.2. And then the curve here is showing you Dune sensitivity over time. So we'll be doing much better with this parameter as well. Okay, so I promise I'm finishing up. So yeah, again, these really intense beams and massive FAR detectors are going to give us a lot of statistics. So systematics are going to be very important. And there's complementarity between these experiments that are going to, help us scrutinize if something does show up different between Dune and T2HK. We'll really be in a position where we can, have a handle on the different systematics from the different experiments. We can scrutinize those, which is, a really good thing. Scrutiny is good. And there also could be, non-standard interactions that could manifest in the signals differently due to the very different baselines. And having these two different experiments is gonna help you pull that apart and see how likely that scenario would be. Of course, I think I've already touched on that, and I haven't, I've really been focusing here on kind of the 3 flavor oscillation framework, but the physics programs beyond that are really highly complementary as well. Proton decay, supernova, neutrino detection, and of course, beyond the standard model before Jay throws his coffee at me. Complementarity there as well. Okay, so just in closing, maybe I've already said all this, so I won't go back, but I also wanted to mention that, you know, in addition to this you know, collaboration that we have and that we should have moving forward between, you know, sort of competing experiments, if you will, we're also collaborating closely with our colleagues on the theoretical and phenomenological side. I mean, this is one example of that. You know, we've gotten some feedback in the recent years about the best ways to communicate results coming out of our data. And for delta CP, you know, a good way to communicate that is actually looking at this Jarlskog invariant, which is a parameterization independent quantity, unlike delta CP itself, which you know, depends on how you parameterize the PM&S matrix. Picture of Cecilia Jarlskog here too, I'd like to leave you with. Okay, sorry that went a bit longer than I thought, but yeah, happy to answer any questions.
Thank you. Thank you, Kevin, for this excellent overview of the accelerator neutrino oscillation experiments. We have time for one question. I don't see any hands raised in Zoom. Anyone? Okay.
So all of the US-based T2K collaborators that I know are now in Dune. So I'm just wondering, what is the future of the US-Japan relationship if now the US side is really pulling toward the local stuff and there is a nice little pool of US-Japan money just to encourage the collaborations, and I don't know what's the future of that.
Yeah, it's a really good and important question. I'm afraid it's a little bit above my pay grade to give a really thoughtful answer, but I can generally say that what I've seen is that there is still strong collaboration between the T2K and Japan programs, in planning these experiments and some of a lot of the R&D to move forward to be able to realize these experiments. I'm not in a position to give you specific examples, but there was actually a talk earlier in this workshop from a Hyper-K colleague who had a whole slide on all of the collaboration that's still going on and will continue to go on as we move forward to these next generation experiments.
Okay, let's thank our speaker again, and we have our next speaker, Will, right? Okay, please take it away.
All right. Hopefully people can hear me. If not, just let me know. All right. So yeah, I'm Will Foreman. I'm at the Illinois Institute of Technology. Which one's laser here? This laser. Okay. I'm going to kind of give an overview of physics at the MeV scale in large TPCs. This will be more focused on kind of the capabilities of the detectors, not so much the higher level physics that they can accomplish. So liquid argon TPCs, how do they work? You've probably seen this picture a few times at different talks throughout the workshop. You have a volume of liquid argon. In this case, a neutrino will come in, produce charged particles in the final state, and those will ionize the argon. Those electrons will drift to pass through by two induction planes, then collect on the final collection plane. And by combining the information from those three planes, you can produce nice 2D and eventually 3D images of those interactions. This is an event display you probably haven't seen yet at the workshop. It's not a neutrino event, but it is from the Lariat experiment, which is an experiment that was near and dear to my heart because it's my thesis experiment. It was a kind of suitcase-sized large TPC that sat in a test beam at Fermilab. And this is an example of a particular event from a charged pion in the beam that came in and underwent this pion charged exchange interaction. And this event is particularly beautiful, I think, just because it kind of illustrates all of the great things about large TPCs. Each kind of vertical line of pixels here is a single wire. The color represents the amplitude of the charge collected at a particular time tick. And you can really see that separation from these gammas that eventually pair produce into E plus E minus showers. And you can see these two kind of gammas point back to the vertex from this pi zero decay. What I'm going to be focusing on for the rest of the talk, though, are kind of identifying and reconstructing these features that you see here circled, which are just really low energy activity from gammas from this de-excitation process, and perhaps neutrons as well. So most neutrino RTBCs, the reconstruction tools that have been developed for them have been tailored for kind of higher energy GeV scale tracks and showers, which fit well with the type of physics that we're trying to do in oscillation experiments. But they are also sensitive to sub-MeV scale physics as well. So I'm gonna plug this LEPLAR group, this SNOMAS working group that I'm a part of. We had a workshop back in 2020, and we developed this white paper that I encourage you to take a look at. It kind of summarizes a lot of various, kind of summarizes the field in a sense. We identified the opportunities that Dune has in this sub 100 MeV regime, and even lower than, and much lower than that actually. We also talk about developing standard signal and background assumptions, and it's kind of a way to exchange ideas between different Dune technical groups. So this is the kind of a range of the energy range of various signals that we look for at low energies in large TBCs. I'm going to start with these supernova and solar neutrinos that kind of occupy a range around a few MeV up to 20 or 30 MeV. These produce events in your large TBC that are, I would call track-like, or a mix of tracks and more point-like sources. So this is, for example, this is an 8-centimeter track from a simulated 20 MeV electron. And you can see a lot of associated low energy gamma activity or blip activity as well in that event. But if you go toward this middle regime, you enter a regime where the events are neither track-like or they kind of, I guess they evolve toward more being point-like sources that are hard to actually track in 3D space. They're just single energy depositions in your detector. This is an example from Joseph Zanamo's talk from yesterday or a couple days ago. Just a 2.5 MeV electron in raw data, and you can see it only occupies 2 or 3 wires, and fairly not as detailed as this for sure. And if you get even lower, if you look at argon 39, for example, these are signals that will only ever occupy a couple channels, or usually just one single wire or pet charge readout channel in your detector. Just to give like a quick kind of overview of what I mean when I'm talking about reconstructing, this is just a cartoon of an MeV scale energy deposition in our detector that will drift toward the wire planes. So what you end up with are 3 kind of sets of information from each plane. These circles here are hits. The blue hits correspond to that actual true charge deposition from this fake cartoon event. And so we match the signals in time between the planes, and then use those wire intersections to get a YZ position of those coordinates. This gets easier and easier as the signals get larger, because then you have a topology to play with and match between the planes. It gets more challenging at lower energy, because then you just have single hits a lot of time, and those look a lot like noise if you have electronics noise in your detector. So this kind of pink match here is a fake noise match that I drew. And we get a lot of those when we try and lower our thresholds. So what I've been working on right now in Microboon is a standard toolset and algorithm in the LAR TPC software framework that we hope to eventually apply to in more general sense for Dune and other LAR TPCs. But I won't be thinking too much about that anymore. I just wanted to mention that here. These are a couple fairly recent examples of large TBCs showing that they can actually reconstruct signals down at this range. I'm going to start with Argonaut. This was basically the Lariat TBC I showed earlier, but before Lariat, it was actually a neutrino TBC in the NUMMI beamline. And what they had this really cool study where they looked for nu mu CC events so they looked for that muon track. And they tried to reconstruct these de-excitation gammas surrounding that vertex. And they found that they could actually reconstruct this fairly well and compared it to two different models here. More recently, I think possibly this or last year, there was this microboon paper where they did an R&D run where they doped their TPC with a radium source, which eventually decays to radon. And through the decay chain, you finally arrive at this decay from bismuth to polonium and polonium to lead. And that process releases a beta of about between 0 and 3.3 MeV or so. And very quickly after an alpha, which is about 7.7 MeV. And in your TPC, because that beta decays and then that polonium just sits there for a while and then decays later, but drift is still happening. So that actually manifests in your event displays as a separated, two separated energy positions. And they developed an algorithm that looked for this type of signal. And they found that if they ran their algorithm on just regular data, or actually when they were doping, but had their filter in place, they found that they didn't really see a rise. When they removed the filter and just had the argon not being filtered and just bypassing that filter completely, they saw a very clear rise in the bismuth polonium signal, which proves that microboon could filter out this radon. But it also proves that they can see signals down at this energy, which is really exciting. So going beyond that, there's some really cool physics you can do at MeV scales, or physics that's enabled by MeV scale physics in large TPCs. I'm going to start with supernova neutrinos. Basically, you need to get to low energies to reconstruct this full expected electron energy spectrum. Tiago's talk, either right after this, I think right after this, yeah, we'll go much more into detail into this. You can also do some cool beyond standard model searches. For instance, there was this milli-charged particle searches that Argonaut did. They looked for isolated blips in their detector, and they pointed them back toward their target. And they were able to place a pretty good limit on milli-charged particle production, because a milli-charged particle will travel through the TPC and only scatter once or twice, and your signal will look like just two blips. There's also some cool topology. You can identify certain topologies using blips in the events. This is an example of just an upscattered dark neutrino that comes in, or actually upscatters to a dark neutrino, then decays later and produces a charged lepton pair that would be displaced from this blob of blips near the nuclear de-excitation from that original neutrino interaction. So your signature would be some blips displaced from a vertex from a charged lepton pair. And related to that, if you do have charged leptons that range out and stop in your TPC, their behavior as they stop depends on their type and also their charge. For instance, negative muons and negative pions will capture at a certain time scale and produce MeV selectivity around your endpoint. So you can use that information as a possible discriminator to tag either mu plus or mu minus, or between muons and pions. And finally, just in normal GeV scale neutrino interactions, there's a lot of hadronic activity that's produced. So you get neutrons that come out and produce lots of MeV scale deposits, and being able to see these around your event can tell you a lot about what happened hadronically in that interaction. I also want to mention neutrinoless double beta decay. You've seen some talks yesterday and the day before, and you'll see one later by Fernanda. But you do need good energy resolution down to 2.4 to 2.6 MeV to be able to resolve this in a large TBC. And And there have been some really cool studies looking at photoionizing dopants to achieve that. We at IIT and some colleagues at Rutgers did this kind of a simulation study using a generic Dune like Monte Carlo to explore some of the benefits that I've outlined in the previous slides. I encourage you to take a look at that paper if you'd like. One of these, I'm going to highlight a couple of them. The first is supernova neutrinos. You'll be able to recover more energy, of course, if you actually include those isolated blips in your event, just in your reconstruction, rather than just the primary electron track. That's pretty much a given. But there are also cool things you can do with channel ID. So you can either get electron neutrino charge current interactions from a supernova neutrino, or you can get flavor inclusive electron scattering neutrino events. And these produce different looking topologies in terms of how many blips are produced around that interaction point and the distance that they are usually around that interaction point. And this is just an example of that electron scattering versus charge current scattering with and without neutrons. And you see a clear difference in the number of blips around that interaction point. And another really cool thing you can do is if you can tag neutrons in a supernova neutrino event, you can, just by the very nature of saying that you had a neutron in your event, you can kind of artificially improve your energy resolution just by the fact that you can say, okay, there was 7 MeV of energy that we lost due to the separation energy of the neutron in K40. So you can see if you just plot the true neutrino energy versus all of the restricted energy in the event, you see this blob that's a little bit displaced from the main blob. And these are the events where a neutron was produced. So you have energy that's lost that you can't reconstruct unless you kind of infer the neutron was there somewhere. Pion muon and separation, I've already touched a little bit on this. Basically, there are differing probabilities of capture or decay with different final states. So you can use that activity of blips as a discriminating metric, and you can think of a variety of ways to use it, most likely in some sort of BDT or machine learning algorithm. And finally, single gamma spectroscopy. So these neutrons that are produced in your events tend to scatter around, and they tend to like producing these 1.46 MeV gammas. And this is cool because this means that in our large TBCs for free, we get a calibration source at the MeV scale. And this is just a simulation where we simulated 10 MeV neutrons, let them either scatter around or capture, and then just did some blip clustering procedure and was able to actually see that 1.46 MeV peak amidst a lot of other activity that's produced by that neutron. So this is exciting. We have a free calibration source and Dune and other large TBCs available to us. So this is my summary slide. I just want to say that this MeV scale reconstruction is sort of the next frontier in neutrino large TBC physics. You've seen a lot of talk about it over the SNOMAS workshop. And again, I'm going to plug this paper from the Leplar group. And this only includes a tiny fraction of that paper. So please take a look if you'd like. And yeah, thank you for listening.
Thank you for the excellent talk. Okay, we have one question. Okay.
Sweet. Could you go back a slide? Yeah, the 1.4. Yeah. So this was just 10 MeV neutrons. So what would that look like if you how prominent would that 1.46 MeV gamma peak be in like a neutrino interaction, like with all the other garbage going around? Like, does it stick out still? Can we do that? Can we do that like tomorrow?
Tomorrow? I can work on it. I don't know, actually. This was kind of like an idealized study where we didn't have any kind of cosmic background. Yeah. I imagine it won't look as nice as this for sure.
It looks really nice.
Thank you. Yeah, that's a good question though.
Okay, so we have another question from Kevin, and that would be it.
Okay, yeah, I was gonna ask about slide 12, the yeah, using the beta decay in microboon. This is yeah, cool. So the flat line around, I don't know, 5 or 6 events, if you were to go back in time, does that stay there? So is that just a background, or is that like a steady state from putting it in and taking it out at the same rate?
I believe the answer is yes. They ran the same selection over various taking periods and found roughly the same rate as a background. This background rate's actually, there's some follow-up studies going on in microboon right now to kind of pin down what this background actually is and try and reduce it more. It's a combination of just noise that tends to produce this topology accidentally. Also, interestingly enough, this beta decay process also produces some gammas, which will kind of manifest as spatially separated. I'm drawing with my laser on the screen, but you probably can't see it. Spatially separated deposits around your beta candidate. And that can also mimic this time separated polonium signal. So part of the background's also from that, where you get accidental gammas from the deexcitation that trigger that, that selection there. And that process happens also with some other of these radioisotopes. So you could be selecting other things as well.
And then I guess that suggests also, the fact that with the filters, you couldn't really see this increased rate, but when you take the filters, I guess that means, you can put the stuff in and then put your filtering system back and it goes away pretty quick, right? So you can not contaminate. That's great. That's very cool. Thank you.
Is it a quick question? We're a little bit running out of time.
All right. This is a very good lecture. I really enjoyed it. Understanding the low energy processes, because the reason why I say so is because as you go as low of a threshold as you can, you actually expand not only in doing these supernova physics, but also in beyond the standard. I'm sorry about saying beyond the standard model, but you actually extend the kinematic reach. For instance, looking for these low mass dark matter or the axion-like particle searches, you can expand it out quite a bit, where energy frontiers cannot cover. So it's a very complementary thing that we can do. Now, looking at this, one of the ways that we can actually extend and lower the threshold is by doping it. So you have a doping, and here is a 4 point some MeV threshold that the energy differences that you can look for. Is there any intrinsic limitations in the liquid argon TPC? Therefore, we may have to replace, say, for example, third or fourth modules of Dune for something that we can reach even further down, or is there we can actually push by adding more doping agent, you can push it down even further. So right now, what is the level? About an MeV? That's the lowest we can go.
Around 200 to 300 keV.
200, 300
Is roughly
keV.
is the threshold right now.
Yeah.
And it depends. That's kind of like our default tools that we use, which are
Default
sort of geared
tools.
toward higher energy stuff. So it's interesting because these TBCs collect tons of information and we throw out 99% of it as we're doing the reconstruction, just to
Exactly.
save disk space and to speed things up. And I think we have to think about better ways to incorporate all that information at a lower level. And I think there are algorithmic ways we can improve our sensitivity without having to.
Are there part of the things we can do, for instance, lowering the the electronic noise?
Yeah,
Is that part of the contributing factor? Because you showed some of these things, right? They show that the blips are there, but they were fake blips, and those fake blips, as I understand, your purple blips were electronic noise blips.
Yeah, so I guess you could work on reducing electronic noise. A lot of that comes from how you filter your signals. There are also ways that we haven't really explored of how to maybe identify those noise-like hits based on their width or their height or the ratio of those two things, and try and cut them out like that.
I mean, one of the ways you did was demonstrating that these hits are timed properly, right?
Yes. Actually, yeah, I drew it with just 2 matches here, just
Yeah.
because requiring that third match pretty much squashes the noise completely, but also reduces your sensitivity.
Right. But these things also impact, the way that we can trigger, right? So therefore, I think it's an important thing for us to be able to, manage these things in a fast way.
Right. Yeah.
Yeah. So there.
Okay, thank you. That's okay. Yeah, okay, we can move on to our next speaker who's going to be online. So Thiago, if you can share your screen and just take it away when you're ready. Okay, take it away. Thank you. We can see your slide, but we can't hear you. Can you hear us? Yeah, we can see that you're unmuted.
Okay.
Yes, we just heard something.
Can you hear me now?
Yes.
Great. I don't know, some settings was messed up. Should I switch on the video or leave that off? Do you still hear me?
Yes.
Okay. And you have the slides back, right?
Yes, go ahead.
Okay, thank you. Sorry. So good morning, everyone. So my name is Thiago. I'm a research fellow at the University of Sussex in the UK. And of course, it's my pleasure to be here and talk to you a little bit about the low energy physics program on Zoom. Unfortunately, online and couldn't be there with you at this time. So to start, let's remind ourselves of Zoom. So I'm quite sure most of you know about it, but the Deep Underground Neutrino Experiment is a next generation flagship neutrino experiment. So we'll create a high intensity neutrino beam at Fermilab directed to a non-axis far detectors 1,300 kilometers away in South Dakota. And we also have a multi complementary near detectors to provide unprecedented control of systematic uncertainties. So the DOOM collaboration aims at fundamental questions on neutron oscillations, nucleon decay, core collapse supernova, and of course a rich ancillary science program. So the fire detectors will consist of 4 modules each in a mine in South Dakota with target mass of about 17 kilotons each. So the first 3 modules will be based on liquid argon time projection chambers housed in huge cryostats, as you can see here in this drawing. Here you can also see a person to give a perception of the scale we're talking about. The 4th module, one of these 2 caves, is not decided yet, but it is an opportunity for new technologies currently under discussion. So in the first phase of the experiments, we'll have only 2 modules operational, as you can see here. So one will have about 3.5 meters of horizontal drift and a wires-based anode, while the other will have 6.5 meters of vertical drift and a perforated circuit board based anode. And of course, both will be equipped with scintillation light detectors as well. So we will use a liquid argon since it's an inert, dense, and naturally abundant element. So as we'll just show you in his talk, this strong electric field applied across the TPC is used to collect electrons produced by the energy loss of the charged particles. So this will produce some bipolar pulses in 2 induction planes and unipolar pulses on the collection planes. And these planes projections is combined with the time information to produce a 3D image. So the liquid argon is also transparent to its own scintillation light, so it can be used as an internal trigger and for complementary calorimeter measurement. So these the 3D images are excellent with millimeter scale resolution over tens of meters detectors. So this is proven by the prototypes running at CERN, exemplified here in this event display, showing a 3DV pion plus causing stopping protons and a pion zero decaying to 2 gammas. So as you can see, we have an excellent energy measurement capability on a total active calorimeter and a powerful particle identification based on DDX, range, and the event topology. So although designed to measure the DV scale neutrino interactions, Dune fire detectors will be also capable to record interactions below 50 MeV, as we will also show you earlier. Such as from a solar and core collapse supernova neutrinos that I'll focus here on this talk. Could have other topics too, but unfortunately time is limited. So the dominant interaction channel for these low energy interactions is the charge current on argon, but we also be sensitive to elastic scattering on electron and neurocurrent interactions. And a way to classify the several types of interactions is by looking at the presence of photons or gammas from the here the potassium, chlorine, or argon. The excitation, so this for the charge or neutral current, or their absence in the case of elastic scattering. Here is an example of a simulation on how the elastic scattering on the three-plane view, so two inductions and one collections, and a charge current reconstructed interactions will look like in Dune, based on very detailed simulations, for example, like in this particle propagation diagram. This reconstruction will be very similar to what we'll already nicely show you in the previous presentation. So I'll move going in another details. So going on to specifics of low energy events. So one of the main goals of Dune is to record a supernova neutrino burst in case one happens during the detector lifetime. So such a measurement was already done in the past with the beautiful results from the 87 supernova, giving tens of events in Kamiokande, IMB, and Baxan detectors. So, and measuring supernova neutrino burst will provide us with a rich information on the collapse mechanism, the time evolution, and if a black hole was formed or not, or if we have a neutron star. We'll learn much about the neutrino physics as well. So, for example, on the neutrino oscillations parameters and their absolute mass scale. So here you can see the expected signal in Dune computed with snow globes in case of a supernova happening at 10 kiloparsecs away from us. So this 10 kiloparsecs, according to some models, is the most probable distance for the next galaxy supernova, supernova in our galaxy. So as you can see, the electron neutrino flavor in green, so here is the neutrino energy, and here is the observed energy in the detector, is the dominant one. And this is desirable since the liquid argon is the only future prospect for a large, clean tagged electron neutrino sample, because all the other large detectors will have a rich electron anti-neutrino sample, such as in the inverse beta decay liquid scintillator detectors. So this is a unique feature for Dune. Of course, the signal scales with how many fire detectors modules will have and how far the supernova will happen, as you can see in this plot. So the expectation is to have at least 100 of events, even if you have only one module operational. But with the possibility to have 1,000 covering up to the glass edges and like tens for the marginal clouds. Unfortunately, any supernova happening in our neighbor galaxy, the Andromeda, is out of reach for Dune, since you have like one event. However, to observe a supernova neutrino burst, we will need a reliable and efficient trigger system. So I want to briefly show you the triggering strategy we are developing here at Sussex. So we start with the online monitoring of the TPC waveform by the firmware of the electronics that will have a pulse like this one when the ionized electrons are collected in the collection plane. So by setting a threshold, we will have a stream of hits. So the firmware will give this hit object, setting the feeding into the triggering software of Doom. And here is the likely distribution of hits we'll have from a supernova neutrino burst. So this is just a heat map. So we have, so for each supernova neutrino interaction, we'll produce tens of hits in this scale. So even if we go to higher energy, in the limit of 50, we have like 40-ish max hits being produced in the detector. So, but this is just hits laying around. So how you get useful information. So the next step is to the clustering of hits, and this is mainly to avoid spurious signal and backgrounds, which we'll cover in a minute. So we'll perform these online data selection, and it's kind of simple. It's in simple terms is an ordering in time and space, where time is given by the channel numbering and time by the clock ticks, and of the hits. And then we apply some tolerance parameters to form a cluster, this cluster of hits. And then, for example, here in this sketch we have two cluster hits, where only one, this green one, is selected due to the cut of at least 4 hits in a cluster. So by having this selection in mind, this is the event selection efficiency that's given by these differential curves in terms of the energy of the parent neutrino. So we can see here the impact of the number of hits requirement. So for example, to select a 10 MeV supernova neutrino interaction, so we can go nearly to 0 for about 90% when we reduce the requirement of 6 hits to 3 hits per cluster. So however, this selection efficiency only tells half of the story of the triggering supernova at Doom, where the other half is, of course, as I mentioned before, the backgrounds, which the main source will be radiologicals. So it's vital for us to understand the radiological backgrounds of Doom, since they will determine what's the supernova fake trigger rate. So here you can see the rate of hits per anode plane due to backgrounds and electric noise. So the first front to reduce this rate is the heat finding threshold, which is very efficient to handle electric noise while reducing the radiological by a factor 2. So this is the model we've been constructing by several sources. But we still have a huge rate to deal with. So the next front is, of course, the cluster selection, which is very efficient to eliminate the backgrounds. So from a megahertz rate, we will have a few hertz at one fire detector module. And this is a very low energy cluster, actually. So by applying a simple charge cut, we can eliminate these two main components due to uranium chain contamination. And at the end of the day, the main source of concern will be the neutron capture rate in the detectors that produce a very similar signal as a supernova neutrino interaction that we'll also show you earlier. So with the rate of background clusters in hand, we calculate the number of clusters in a 10-second window, which give a fake trigger rate of about 1 per month, which show in this plot using Poisson statistics. So we have that about 13 clusters should do the trick. And this fake trigger rate of 1 per month is the current requirement of Doom due to constraints of buffering, data transfer, and on-site data storage. So, okay, with this requirement of 13 clusters in 10 seconds and the signal efficiency I've shown you earlier. So this is the supernova triggering probability using the Rooder-Pool model in a range of distance. So for reference, this is the distance of our galaxy edge and the Magellan clouds from us. So with at least 4 to 6 hits per cluster, we're able to trigger supernova anywhere in our galaxy very efficiently. And yeah, I agree that the efficiency for the Magellan cloud is a bit bummer, but we still have a room for improvement. So we can improve the trigger efficiency, specifically for the supernova happening in the Magellan clouds, as the 1987 one, by using the charge distribution of the cluster that I haven't told you much about yet. So how we do that? So we can compare a distribution containing the signal and background to one distribution with only backgrounds, and then through a likelihood approach, we can increase the efficiency from about 10-ish% to about 70% when you have these fake triggers 1 per month. So this is what we call a shape-based trigger, since you use this charge information distribution in construct to the counting method that I showed before. Of course, we can also use the light detectors I mentioned, but didn't go to the detail, but we can use them to trigger supernova using the scintillation light signal. And actually, the light detectors, the light detection will be crucial to give the T0 of the interactions, since the light signal is much faster than the TPC signal. So how faster? It's about 1 million times faster, to be more precise. We talk about a nanosecond scale versus a millisecond scale. We still have a little bit more room for improvement. So in the pipeline, so far I've shown you results using only the unipolar signal from the collection planes. So we are also studying how to include the bipolar signal from the induction planes in the triggering. So we can do this by an online conversion of the pulses. So as you can see here, the original raw waveform bipolar and converting them to unipolar. And then we can apply the same heat finding method I showed you before. So these induction heats may allow us triggering based on region of interest that can reduce the data rate. So by reading out only specific parts of the detector subcomponents. And of course, additionally, with more hits, we can also improve the trigger efficiency. As I said before, then the detection of electron neutrinos is a unique feature of the argon detector. So once we can trigger the supernova, we may be sensitive to this neutronization phase that, from the electron neutrinos, which can be used to possibly determine the neutrino mass ordering, exemplified here in this plot, where we have a suppression of the normal ordering scenario. So from the reconstructed spectrum of the supernova neutrino, we can also retrieve neutrino mixing parameters and also other information such as neutrinos, self-interactions, and absolute mass, and the absolute neutrino mass, and so on. So the time and energy information of the interactions will also be used to understand the stellar evolution and the explosion mechanism, and whether a black hole was formed, as I said, so just to validate the models. And just to stress the obvious that we can just miss the detection of the next supernova. So just changing gears in this next couple final slides to solar neutrinos. So Dune will be sensitive to the boron and HEP fluxes from the sun. As for the supernova, the charge current is a dominant channel, forming tracks and a gamma cascade in the TPC alongside with the light signal. Triggering is a challenge due to the large background that several MVs Eva showed you earlier. So how large, you're wondering again? So we can have a look on the CNO flux that recently nicely measured by our colleagues from Borexino. So in June, the CNO flux will be buried by a factor around 1,000 by radiologicals. So we really have to push to high energies. That's why the boron and HEP fluxes is more suitable. But we indeed have a few ideas to overcome this challenge. They exist, and the more in the context of the fourth opportunity module. So I invite you to check this reference with details of how a low background liquid argon TPC would be feasible. So nevertheless, we still measure the high energy solar neutrino fluxes. We'll give information about the square mass splitting to one from the day and night effects as done by the other experiments. So this measurement may push the current tension between supercamilcan and no to Camilan to possibly 5 sigma. So just looking at these high energy tails here. And with this, I come to the end of my talk. So I hope in the last 18, 19 minutes, I could show you that beyond precision measurement of neutrino oscillations, DUNE will provide a large data set of astrophysical neutrinos. Argon detectors uniquely sensitive to the electron neutrino flux, electron neutrino flavor flux, with a large mass and excellent tracking, and a huge phase potential in the early running. So we can, of course, do that. Even don't need to wait any beam as soon as the far detector are ready. Thank you.
Thank you for the excellent talk. Are there any questions? We have time for only one question, though. Sorry about that. Are there any questions? Any one question, sorry.
Hey, Thiago. Do you know some of the details about the measurements of the neutrino mass hierarchy and the oscillation parameters? Because it sounds really fun that just with one event and we're done.
No, yeah, we need the spectrum information. So yeah, sorry, I didn't show you here, but for example, the mass ordering, not on the spectrum, but on the time evolution. So for example, here we have this peak of neutron on the neutronization phase of the supernova, that when we apply oscillations, it reduced but in the inverted scenario, and the normal ordering is suppressed. And then on the parameters, and then we have to also look on the energy distribution. But yeah, because it changes over time, but then we have to study to show how these will vary against the different scenarios and models.
Okay, thank you. So we'll move on to our next speaker. Thanks, Thiago. And Fernanda, we have the speaker over there.
Awesome. Am I audible on Zoom? But thank you for those of you who are in the room and said yes when I asked if I was audible.
Okay, Fernanda, take it away.
Am I good? Okay. Awesome. I'll not sure that I can be too short, but I'll do my best to release you for lunch as soon as possible. But I am excited to talk about doped liquid argon TPCs as a neutrino double beta decay platform. So I'll tell you a little bit about that. And what you'll see in this talk today is based on this paper, which it's on arXiv now, and we've submitted to PRD. And once we stop giving talks as NOMAS, you likely will see in published soon. Okay. I think my slide advancer is not doing what I want, but I don't know if that was you or me, but thank you. Okay, so here's the takeaways from this talk. And neutrino is still double beta decay discovery. would elucidate questions about the neutrino mass mechanism and limits to the half-life for neutrino double beta decay are intertwined with the question of the neutrino mass ordering. So it's an interesting question to go after. And what I'm going to talk about today is how dope liquid argon TPC could enable this and also significantly expand the physics scope of LAR TPCs in Dune phase 2. And it's also compatible with other concepts for looking for low energy signals. Lastly, the especially interesting thing about this concept is that there are a bunch of R&D questions. So there's a big R&D program that that spans from the questions that we want to answer with this. A few things to reference are the paper that I talked about, but also our LOI for SNOMAS and 2 talks that already happened this week about photosensitive dopants. So I'm not going to go too much in detail on those. After the talk, when we're out, we can ask questions, and I'm sure at least Joseph can go into a lot of detail. All right, so searching for neutrino double beta decay is a little bit different than what we're used to if you're usually doing analysis on a LAR TPC. The first challenge is that if you think about the energy range of phase 1 Dune and even some of the stuff we've been talking about in the previous talks, right at the lower energy edge, one of the things you get is you find this neutrino double beta decay if you can make it happen. The other thing is, the other important thing to point out is that the signal for neutrino double beta decay is the 2 electrons from the decay. And the most important background is often the irreducible background from 2 neutrino double beta decay in the same isotope. In that case, the signal for both is the 2 electrons. And you need to measure the energy very precisely to see if you have 2 electrons with some energy that went into creating the 2 neutrinos, or you find the energy available to go into leptons, or what we call the Q value, exactly in only the 2 electrons, and there are no neutrinos. So this is from here you see already that energy resolution is going to be important, and I'll tell you what other things are going to be important. And essentially we need to make work if a concept like this would happen. So again, the goals of this concept are to enable neutrino double beta decay searches in LAR TPCs with sensitivities beyond the ton scale neutrino double beta decay experiments, well into the normal ordering region of that phase space. Will show when I show sensitivities in a little bit. And the 2 main parts of this concept is doping with xenon 136, which is the candidate isotope for the decay at 2% is what we assume, and doping with a photosensitive dopant to enable this very good energy resolution at low energies. Okay, I'll say one thing about xenon to get it out of the way, because this is often the first question, and reasonably so. What we know is that we likely can dope with xenon at 2% because that's been demonstrated. And there, a lot of people working on xenon doping are thinking about the changes in scintillation profile, but nowhere near at the scale of 2%. There is a challenge in that the current production of xenon is something like 60 tons a year. And there are references, I think I have them on the backups, and if not, I can add them after this talk, to research that's ongoing, and promising avenues outside of our field that indicate that this is promising to some extent, if you believe the trend of how we are increasing the production of xenon over time. That's all I'll say about xenon. But I'll tell you how we model the backgrounds for this concept, which is where our other constraints come from. So we model this backgrounds using RADPAC, and we assumed a monolithic simple fire detector module with normal material. So nothing is low radioactivity at this point. And the there's several categories of background, and I'll at least talk about the ones that can kill you or experiment, not you, although some are both. So which are argon 42. It's really potassium 42 decay from the argon 42 in the liquid argon. Radioactivity from the detector and external to the detector, and the especially pesky are the neutrons that penetrate deeper into your detector. But there's also other sources of background that I'll mention in a couple of slides. Okay, so there are a couple, I would say, main strategies that reduce most of those killer backgrounds, and they're applied in a different order above and below. So just in case this is confusing, but if you see the plot above, you'll see that we assume depleted argon, which is the, you if you eliminate the argon 42, which is the one of the most worrisome backgrounds out there, you're left with that. And if you add fiducial ascension, then you end up with the middle bottom plot here. The argon 40, the depleted argon is compatible with what people are thinking for dark matter experiments, etc. So we've heard a couple of talks this week about underground argon. And the additional thing that we assume here to get us from fiducialization that gets rid of some of that radioactivity external and from the cryostat to the numbers that we see at the bottom of the top plot is shielding, and we assume 1 meter water equivalent, which is compatible to what has been proposed to enable the solar neutrino program. And this is, I mean, there's a lot more detail in the paper, but there are, after these main strategies that get rid of those of the killer backgrounds, there are a couple other strategies for some of the other categories of background that I've grouped here. We heard from Will a little bit about this coincident polonium tagging from the BIPO decays, and there are mainly all we assume apart from that is coincidence, like the photon coincidence in 32 centimeters around signal candidates that deals with some of those Placian backgrounds, and the same for around muons that were 2 meters for a 60-second window of all muon tracks to reduce some of this other installation backgrounds as well. So I grouped the remaining large backgrounds that you'll see into these categories, and I'll show you in more detail what they look like after those assumptions and how we are going to reduce them. And here again, the signal is in neutrinos, the beta decay signal is in red, and you'll see that with these assumptions, we've reduced the background sufficiently that the first thing we have to worry about is the 2 neutrino double beta decay. And that's where the energy resolution matters, because if you look closely at this plot, you'll see that I assume at the top right 1% energy resolution at 2.5 MeV. And if I move that even to 5%, which is the lower plot now, you'll see that this picture looks much different. In fact, the plot on the left is the counts in the region of interest, but that's between the dashed lines on the other two plots versus the energy resolution. You see that before, if you need to be below something like 3% energy resolution before the 2 neutrino double beta decay starts to eat your signal, right? So when below 3%, but hopefully 1% energy resolution is essential for this to work. And in that case, we have to think about how we collect most of the information, and what the best way to do this is if we want to really squeeze out the improvements in energy resolution. And as you know, we have 2 signals available in our LAR-TPCs, and at the typical LAR-TPC field strength, we're going to expect to break down around 50-50-ish. And this is especially important in low energies because if you think about the signal that's going to hit one or two of your wires, let's say, you're now going to have the topology information, et cetera, to work with, right? So one thing that it becomes evident is that combining the information from the ionization and the scintillation is going to be important, especially if you see the sum on the bottom plot. The sum quanta is much narrower in spread that if you just look at the scintillation photons or the ionization electrons, and this is for a simulation of 2.5 MeV electrons in RTPC. Okay, so how well do we have to collect the light, which is not, and how well do we have to collect the light to get to those levels? And what I'm showing on the top here is using the NEST simulation. What you're seeing is on the y-axis, what energy resolution could be achievable for different light collection efficiencies in the light in each colored line. And on the x-axis, Dune's going to sit in signal to noise ratio, like somewhere out of or below that line that I've drawn on this plot here. So to get to 2 or 1% energy resolution, you need at least 20, maybe 50% of the photons per MeV. And that is a lot for big large TPCs. State of the art, the best we have done so far is an SBND. While reflecting some of the light, et cetera, we've been able to get across the detector volume something like 160 or fewer photons per MeV. So that's much below what you would need, and that is where the photosensitive dopants come in. And the idea here, again, we have given a couple of talks this week about photosensitive dopants, but the idea here is using this class of hydrocarbons that there have been some demonstrations for, and what they do is they turn some of your light into charge, either by photoionization or Penning transfer. And and what you're seeing here is a simulation, and if the x-axis is, if you wouldn't mind moving the legend, that'd be fine. But if not, that's okay. You just have the electric field, and the Dune electric field at 500 volts per centimeter is marked there in purple. But you see for the for doping at the less than 100 parts per million, the comparison here on the charge that you collect from the blue, which is in the liquid argon, to the green is you see that we expect a order 9 times enhancement. So it's a good indication that R&D to confirm this in the Dune environment with the signals that we'll be looking at 2.5 MeV will be a good place to start to look into what doping scenarios will be best and what we actually can accomplish in terms of enhancement of the energy resolution. Additionally, something that we've seen in studies done by Icarus, where they doped a 3-ton prototype with PMG at the less than 10 parts per million. They saw an increase in the charge collection, but also a more linear detector response with the doping. So if you think about potential effects of adding the doping to Dune beyond what you could enable in neutrinos double beta decay, you'd have a more linear detector response, lower thresholds, better energy resolution for highly scintillating particles like alphas and nuclear recoils, and also the low energy hadronic, the low energy components of GeV neutrino interactions as well. Okay, so I have a summary of the requirements, and I showed you this before. You need below 3% resolution, depleted argon, and an external shielding. Now these can move around a little bit. We used some conservative assumptions, but in the analysis, we noticed that, I mean, the depleted argon is a hard requirement to make this concept work, but there are a couple, like what exactly amount of xenon you need, and whether you need the external shielding, and how close to 1% energy resolution you want to get the sensitivity that I'm showing here. What I'm showing on this plot is the sensitivity to M beta beta, and what we do is a counting analysis, assuming 2% xenon-136 and 10 years of running, and 1% energy resolution on the lower pink dotted line, and the pink dashed line has the same for 5% energy resolution. And you see that's well within the normal ordering region of this plot. And I've marked the expected ton scale, well, five ton scale future neutrinos double beta decay experiment sensitivities to that plot as well. But what I claim is that some of the assumptions can vary a little bit and still give us sensitivities between the 2 and 4 millieV. And I'm going to leave you with some of those in my summary slide, where I essentially have the sensitivities that I just showed you with the base assumptions. But on the bottom, you see that varying energy resolution, the exposure, and the amount of xenon you have, and importantly, the fact that you can go almost like an order of magnitude and still touch this gray band that corresponds to where the normal ordering region of that plot starts. So there's some wiggle room here, but this concept, we have to do the R&D to answer some of these questions, but there is some wiggle room on some of these requirements. And out of the very difficult things that we need to make converge for neutrino double beta decay to be possible on a Dune phase 2, the road there includes a very rich R&D program, and like I mentioned, concepts that are compatible with other Dune low energy concepts as well. Thank you.
Thank you, Fernanda. Are there questions in the room or Zoom? And thanks for people to stick around. No, doesn't.
Oh, good.
Hi, so I'm just curious when you add the scintillator for extra light, does that also improve your high energy signal? And
you mean that the dopants for the
to get better
light,
energy resolution?
Right. So when you add the dopants, you'll turn some of that light into charge, and then you'll improve the low energy stuff. But if you think about it in terms of, say, the low energy components of GV scale neutrino interactions, you're probably going to enhance what you can do with those as well.
So like your threshold for proton trafficking might go. No, it wouldn't change the charge collection, I guess. That's my question. Does it?
Well, you get more charge.
You do get more charge.
Yes, because what happens is that charge to light ratio is what gets modified with the dopants. So you're not going to get that 50-50. You're going to get mostly charge and little or no light left. Mm-hmm.
Thanks.
Okay, one more question.
I'm not sure if this, I haven't really thought this one out, so this might be a silly question, but would, in terms of understanding the background, would you gain anything by perhaps like segmenting this detector and having part of it doped with xenon and part of it not doped with xenon?
So something that, for example, you can do in neutrino double beta decay experiments is that even if they're just the isotope, you can do depleted versus enriched xenon, right? So that would tell you something about the backgrounds in terms that one has 90% xenon-136 and the other one like 5 or 10%. You can do something similar either by introducing the xenon, but what you're talking about, segmenting the detector is something that if you could do, that probably also make a difference to like how much you need to fiducialize and how much xenon you need. Because if you see some of this, I have 2.5 meters is what we use for that sensitivity. But yeah, if you change your need to fiducialize, or you've already done it with an internal volume, let's say, then you would need a lot less xenon for the same measurement.
Thanks.
Okay, let's thank all of our speakers and everybody who asked questions. And